Hi everyone. Today I'm Adam. So today I'm going to go over the second part of probability. So I'm just going to stop just before we get to kind of Z scores and things. So everything up to Bernoulli trials I'm going to cover in this video. Okay. So one of the things in probability is that a lot of students that I've taught have gotten confused about is basically like, when do you add probabilities and when do you multiply? Because we're going to see now for all of these, I'm basically going to like multiply the entire time. And it's just like, okay, how do you know that? So if you kind of, the easiest way that I find is that if you've no idea what's going on, this is kind of your best bet. Basically, if you say the word and, then basically this means you should multiply. But if you say the word or, then you should add. Okay, so if I said, what's the chances that I get heads and then tails? In that case, you would multiply. But if I said, what's the chance of me getting a head or a tail, then you would add. Okay? So that's basically, that's kind of like a good way to just have a quick look at it and just be like, okay, that's kind of what's going on. All right? So we'll see that now in a second. So I'll just go through a quick example. So it says 3 cards are chosen at random from a standard pack. So remember, a standard pack of cards has 52 cards. Okay, so no jokers. Find the probability that all 3 are kings. Okay, so you have 3 things. So first of all, what's the chance that the first one is a king? So the first one, there's 4 kings and there's 52 cards. So the chance that we get a king the first time is 4 out of 52. Great. Now, so let's say you picked a card, that's fine. Now you're picking another one. So what's the chance that the next one is a king, given that the first one was a king? So you picked the king, so 1 king is gone. So there's only 3 kings left. But again, 1 king is gone, 1 card is gone, so there's only 51 cards left. Okay? And then now that you've picked another king, that means 2 cards are gone, and 2 kings are gone, so there's only 2 kings left, and there's only 50 cards left. Okay? And now again, this is the thing where here, you multiply these probabilities, and you'll get 1 over 5, 5, 2, 5. Okay? That's not very important, but, you know, it's there. But basically, the main thing to say here is that here we're multiplying. Why? Because you said, okay, so what do I need to happen? I need to get, the first card needs to be a king, and the second card needs to be a king, and the third card needs to be a king, and therefore we're multiplying. Okay? And obviously, we're minusing 1 every time, and we're also minusing 1 every time up here. Because once you pick a king, a king is gone, but secondly, you had 52 cards, the king is gone, so you have only 51 left, and so on and so on. Okay, so that's another thing to remember. All right? The next bit says, none of the 3 cards are a king. So if none of them are a king, that means now, so here we said there are 4 kings, that means there's 48 cards that aren't kings. So we have a 48 out of 52 chance that the first one is not going to be a king. Great. But now the second one can't be a king either. So now all of a sudden we've picked a card. So there's 51 cards left. 4 of them are kings, which means there's only 47 cards that aren't kings. And then the same thing here. Just like that. So it's 4, 3, 2, 4 over 5, 5, 2, 5. Like that. Okay? So again, the number, how do you go from here to here? You're just minusing 1 every time. And the same here. Okay? Now, the very last one, it says, at least 1 is a king. Okay, so now think about this. What did we just calculate? This is the probability that none are kings. So now you're being asked, you're saying, okay, well, what's the chance that at least one is a king. So if at least one, that means either one is a king, two are kings, or three are kings. Okay? So the easy way to do it is say, oh, well, I know the total probability is 1. The probability of me getting no kings is 4, 3, 2, 4. And therefore, if I minus these off, I have to get the chance that I get at least 1. Okay? So hopefully that makes sense. That obviously, if I said, if I told you that, you know, I got one or more kings, that means that you definitely didn't get no kings. Okay? So basically you're saying that this didn't happen, and therefore that's your probability, your total probability, you're minusing it off because you know that didn't happen, and then you're left with this. So this is the chance that you get one king, two kings, or three kings. Now you could have also found the probability that you get one king, added it to the probability of you getting two kings, added the probability of you getting three kings, and you would get the same answer. You would get 1, 2, 0, 1, 5, 5, 2, 5. You would have gotten the same answer. It just takes a lot more work. So this would take an awful lot more work. And therefore, that's another thing with probabilities, that like, if you're sitting there in an exam and you don't have a lot of space to do out a question, and you're sitting there and you're like, oh my God, I have so much work to do. Sometimes you don't. Sometimes it's just simple like this. I'm looking for, what's the chance that at least one is a king? Well, what's the opposite of that? That means what's the chance that there's none are kings? We already calculated that out, so I can just do 100% minus that chance, and that's it. Okay? Now, for the fourth part is actually quite hard. Okay? So basically, you're looking for the probability that exactly 2 are spades. Okay? So basically, I need the probability that 2 are spades. So that means I need spade, spade, not spade. I need spade, not spade, spade, and I need not spade, spade, spade. So I want to know what's the probability of these. Okay? So first of all, what's the chance that I get a spade? So a spade is going to be 13 out of 52. Then I need to get another spade, but now there's only 12 spades and there's only 51 cards left. Okay? And now, so there was 39 cards that aren't spades. We've chosen 2 spades, which means there's still 39 cards that aren't spades. But there's only 50 cards that are left. Okay, so that's a little bit tricky. So here, you're saying you picked a spade, there's 13 of them. Now that spade is gone, so there's only 12 of them left. So you've 2 spades are gone. But that means you still have 39 other cards, because you still have 13 clubs, 13 hearts, 13 diamonds. So you still have 39 other cards, but you only have 50 cards left because 2 cards have been picked. Okay? And you can probably imagine, for the other 2, it's the exact same. It's just 13 out of 52. Now you have to be careful, because this one is not spades are in the middle, which basically means that you get 39 out of 51 and then 12 out of 50. And then here it's going to be 39 out of 52 times 13 out of 51 times 12 out of 50. So you can see these numbers are always the same, because that's how many cards you have, because all you're doing is picking cards. So of course, that's what's going to happen. Okay? So that's just another thing to just note, that the bottom number is always the same. Okay? So this, so then this, what you do is you add all these together, and you will end up with this. So multiply all these together and then add them up. And just bearing in mind, this is actually the same. So this one is the same as this, and this is the same as this. So all three are the same, which should make sense, that the chance of getting 2 spades and 1 not spade in any order should be the same. That the order, it's not like you've twice a chance of getting a spade first than you do of getting a not spade and then 2 more spades. It shouldn't make a difference, and it doesn't. Okay? All right. So I think that was actually a very good example. Quite hard as well. So yeah, I think we can leave that one where it is. Okay, the next thing that we're going to go over is tree diagrams. So a tree diagram is basically you just draw the different things that can happen. That's kind of what's going on, okay? So an example, so the best thing to do is just an example, okay? So it's, the table shows the ages and gender of 28 students in a school. So these ones are 17, these ones are 18. These are boys, these are girls. Okay? And then basically it says 2 students are chosen from the group at random. Find the probability that 1 is a girl and 1 is a boy. So basically, when you're doing this between girls and boys, what you're doing is you're saying, okay, so what happens is, here you have, and you're making a choice. You can either get a boy, or you can get a girl. So first of all, what's the chances that you get a boy? So how many boys are there? There are 12 boys. And how many people are there in total? 28. How many girls are there? 16. Out of 28. Okay? And just remember, if you add these 2 together, you get 1. Always. So just remember that. That's a very thing in probability, that a very important thing, that things will always add up to 1. They should add up to 1. All the probabilities, if you look at all the outcomes, you have to get 1. If you look at a dice, the chance that you get a 1 is 1 in 6, a 2 is 1 in 6, a 3 is 1 in 6, 4, 5, 6 are all 1 in 6. If you add up all those together, you get 1. Because if you roll a dice, you have to get 1, 2, 3, 4, 5, 6. Same thing with heads and tails. Heads is 50, tails is 50. If you add 50 and 50, you get 100%. So you have to always get 1. So that's a big thing to know. And then this is what a tree diagram is. It just means you just kind of draw out the 2 different options that can have. And then you do it again. Because then you can always get a boy, and then a girl, and then you can get a boy and a girl. Okay? So now, the boy has been chosen, so there's only going to be, what's the chance of you getting a boy again? It's 11 out of 27. Okay? This one is going to be 16 out of 27. Okay? So, because I've chosen a boy first, 1 boy is gone. So instead of 12 boys, I only have 11 now, because I can't choose the same boy twice, obviously. And then down here, it's going to be 12 out of 27 and 15 out of 27. Okay? And again, if you're not too sure, again, if you add these up, you get 1. And if you add these up, you get 1. And that will always happen. Okay? So now the way you do this then is you say, okay, well, this one is the boy, chances of you getting a boy. This is a boy girl. This is a girl boy. And then this is a girl. You multiply the probabilities. So for the first one, I'm going to multiply this by this. Okay? So the chances of me getting a boy and a boy it's going to be 12 over 28 times 11 over 27. Okay, so I get 11 over 63. Like that. Okay? Chance of getting a boy and then a girl, it's going to be 12 out of 28 multiplied by, here we have 16 out of 27. So it's 16 out of 63. Then chance of getting a girl and a boy is going to be 16 out of 28 times 12 out of 27, which is going to be 16 over 63. Again, these two things are the same, which of course they would be. The chances of you picking a boy and a girl or a girl and a boy have to be the same. It shouldn't make any difference which comes first. Okay? And then for the girl and the girl, it's going to be 16 out of 28 times 15 out of 27. And that comes out to be 20 out of 63. Okay, so sorry, 20. Sorry, I might just get rid of that. Like that. And just for reference, if you do 11 plus 16 plus 16 plus 20, you will get 1. Because obviously if I pick two children, I have to get either 2 boys, 2 girls, or 1 of each. Okay? And so, to go back to the question, it says, what's the chance that you get 1 boy and 1 girl? You would look here, you'd say, well, this is 1 boy and 1 girl, that's 1 boy and 1 girl, so it's 16 over 63 plus 16 over 63, which is 32 out of 63. Okay? And that's it. All right? And so now, the next thing it says, find the probability that both have the same age and gender. So basically, when you choose them, what's the chance that both of them have the same age and gender? Okay? So now, in your probability tree, what you do is, so now you have, as we did before, you have 4 outcomes because you care about the age. So here we couldn't care less what the age was, but now we do care about the age. So you can have 17, 18, boy, girl. So you can have boy 17, you can have boy 18, you can have girl 17, and you can have girl 18. Like that. Now, again, for the boy 17, there's only 4 of them. So his probability is going to be 4 out of 28. For the boys 18, they are going to be 8 out of 28. The girls who are 17, it's going to be 6 out of 28. And then for the girls who are 18, it's going to be 10 out of 28. And again, if you add up 10 over 28, 6 over 28, 8 over 28, 4 over 28, you will get 28 over 28, which is 1. Okay, so just be careful. And again, I want to find the probability that both have the same age and gender. So that's the first one. If they have the same age and gender, so again, up here we did all of them, which we didn't have to do. We didn't have to calculate this one and this one. I just did out the full thing just to give you, a better picture of what a tree diagram would look like. But here, it would get very, if you did out 4 of them, it would get quite messy quite fast. So I'm only going to put in 1. Because this is the only one that I actually care about. It's the boy in 17. And what's the chance of this happening? It's 3 out of 27. Why? Because you've already picked one of the boys who are 17. There's 4 of them, so you've picked one of them, so there's only 3 left. And you've picked a student. There was 28, there's only 27 left. Okay? Same thing here, it's going to be 7 over 27. This is going to be 5 over 28. This is going to be 9 over 27. Again, you multiply these, so it's going to be 4 over 28 times 3 over 27. That's going to be 1 over 63. You have 8 over 28 times 7 over 27. That's going to be 2 over 27. You have 6 over 28 times 5 over 28. Sorry, those two are wrong. No, sorry, just this one. Sorry, obviously that should be 27. Because I picked one of the students, so I'm 1 less. Okay, so sorry if that was confusing, that was a mistake. Okay, and so you do this, and this, and then you're going to get 5 over 126. And then the final one, it's 10 over 28 times 9 over 27. That's a third, so it should just be 5 over 42. Okay, and then again, if you add all these up, you will get 47 out of 189. Okay, so that's how you do your tree diagrams, like that. Okay. Okay. All right. So the next thing that I want to do then is I want to go over so I want to go over the expected value. Okay. So the expected value is just a very important thing. If you're running a lotto for a charity, you would have to look at the expected value. The lotto in Ireland, look at the expected value. This is one of the main reasons that I personally discourage anyone from playing the lotto. It is, and gambling as well, it's because of your expected value. Okay, so this is how, if you're wondering, how is it that, someone like Ladbrokes can have all these different bets and all these different odds and tons of things, and it's almost every single weekend for every single match, they're always gaining money. You will sit there and say, that's weird. Surely there'll be a few weekends that they'll lose money on. If there's a big upset in a fight or this, that, and the other, how is it that it's just so often they come out on top? This is the reason. This is what they calculate, the expected value. So the expected value, which is E, is just equal to, so the sum. So remember this symbol? It just means adding. You just add up all these. So it's the sum of the outcome times the chance it happens. Okay, now this will look really, really weird, but I'll do a couple of examples and it'll be quite easy. Okay, so the expected value for something like this. So let's say it's €5 to play. And here's your wheel. So you have your kind of mystery wheel, like so. And you spin around, and it's a fair wheel. So here you have a fiver. Here you have 6, and here you have 4. So the question will be phrased something like this. It'll basically be like, is €5 a fair price? So by fair, what they mean is that if you played this 1,000,000 times, would you expect to break even? Because that's fair. If you can do it a load of times and you have like an advantage, that chances are you're going to win money, then that would be an unfair game because it's biased towards you. The same thing if you were playing this game loads of times and it was biased against you, that would also be unfair. So the expected value of this wheel is just, again, the outcome or the amount of money times the probability that it happens. Okay, so the expected value, E, for this wheel is going to be, so first of all, €4. €4 multiplied by what? What's the chances that it happens? A half. Why is it a half? It's a half because this is 180 degrees. And 180 is half of 360. And therefore, if you spin it around, half of it is on €4. Okay? Then these are 90 degrees, which means they're a quarter. So it's 5 times a quarter plus 6 times a quarter. So this will give me 2 plus 1.25 plus 1.5. This will give me €4.75. So my expected value for this game is €4.75. So basically, what you're kind of saying is you're saying, okay, so if I played this game, on average, I'm expecting to lose 25 cent every single time I play. So now, can you ever lose 25 cent whenever you play? No, that's not what I'm saying. What I'm saying is that if you played it 100 times, on average, you're losing 25 cent per game. So if you played it 100 times, you'd expect to lose 25 euro. That's kind of what this thing is about. So yeah, if you play it once, you might win €1, you might break even, you might lose €1. But because if you look at the wheel, the chance of you losing €1 is twice as likely than you winning €1. That's why this game is unfair. Okay? Because your chances of winning are less than your chances of losing. Okay, so again, this is why, like the lotto in Ireland, that's why you shouldn't buy tickets, because if you buy a ticket, you buy it for €2, your expected value is €1.90, €1.80, €1.50. It's just less than it. Okay, that's why the lotto can make money out of it, because they sit there, they do these probabilities, especially with a lotto, because the lotto, you know what's going to happen. Because all you need to do, like, if I say, okay, I'm going to do a raffle and the grand prize is €100 and the tickets are €1, well, if I sell €1,000 worth of tickets, I'm only giving up €100 worth of prizes, and therefore I'm guaranteed to win €900 or to make €900. So yeah, some person who paid €1 will win €100, but like, I'm after making 900. So that's why the lotto isn't a thing I would recommend people to do. Okay, it's simply that. The same thing in casinos. If you go in, you're always going to be, the underdog in the probabilities. Okay, and in the long run, that's why typically you'll see a lot of people, even if they do start out winning, eventually they will lose, because this expected value will catch up to them, because you're expecting to lose every single time you play. So yeah, you might win a few times, but in the long run, if you play 100 times, you are just going to lose. Okay? So that's expected value. I'll do one more, just if there's any kind of hard ones. Yeah, I might do this one. So it says, so a random variable x has the following probability distribution. That's a lot of fancy words. It's just, listen, you have some variable x, which could be, in here our variable would have been the amount of money we're winning, because that changes every time. So here you have x, you have the probability that you get x, and so it's 1, 0.1, 2, A, 3, B, 4, 0.2, and then 5 is going to be 0.1. And it says, given that the expected value is 2.9, find the value of A and the value of B. Grand. So here it says, because your expected value, E, is equal to 2.9, well, what is the expected value? The expected value is just this number multiplied by this. So 1 times 0.1 is 0.1, plus 2 times A is just 2A, plus 3 times B is 3B, plus 4 times 0.2 is 0.8, plus 5 times 0.1 is 0.5. So 2.9 is equal to 0.1 plus 0.8 plus 0.5 is going to be 1.4, plus 2A plus 3B. So I bring the 1.4 over, I get 1.5 is equal to 2A plus 3B. Okay. Now, again, this is a thing that if some of you have watched my earlier videos on kind of the first chapters of paper 1, hopefully you know the answer to this. If you haven't, then you mightn't know it. But there's 2 things in this equation I don't know. I don't know A and I don't know B. I now have an equation in A and B. That's fine, but it's not enough for me to solve it. So my question is, what do I need to solve it? So I have one equation, but that isn't enough. I need 2. Okay, so I need 2 equations. So there's another equation that I need to make or figure out to solve this question. Okay? So it's something to do with these. And you can try and think about it. But if this comes up in a leave insert, this could definitely be a thing you would be expected to see. And it's to remember that all the probabilities will add up to 1. So if I add up all the probabilities, I'm left with A plus B plus 0.4 equals 1. So A plus B equals 0.6. Okay? And so then I can say that, well, B has to be 0.6 minus A. Plug that up in here. Minus, it's just minus 3A, yeah. So that's going to be 1.8 minus A. So I get A is going to be 0.3. And then B also has to be 0.3. So that's A and B then. Okay? All right. Okay, so I think that's fine. So it's just remembering that because there's two things you don't know, you need two equations. Here's one, and then I was able to make another. Okay? By remembering that all the probabilities will always add up to 1. Okay. So again, independent events, this is like another thing that you kind of, yeah, so this is just a thing that basically the probability of independent events happening together. So the probability that E and F happen together if they're independent is just this. Okay? I'll just do a quick proof. So the probability of E given F is equal to the probability of E intersection F over the probability of F. But what is this thing equal to if E and F are independent? So remember, the outcomes are independent if it doesn't matter if one or the other happens. So the probability of it is still the same regardless of what happens with the other one. So I've kind of given it away with that statement, but basically the probability of E given F is the same thing as the probability of E. Okay? So basically what you're saying is it's kind of like like independent events would kind of be like if you were doing like a maths exam and you couldn't solve a problem, and I came in and I said, oh, it's rainy outside, you'd be sitting there and saying, that doesn't help me in the slightest. That's kind of what this is. It's kind of like you're looking at the probability that E happens, which could be like maybe your car breaks down, or you're flipping a coin and you get heads or tails, and then I just tell you something random, which is, oh yeah, F happened, which F could be like, oh, I don't know, I cooked grass today, or like it's sunny, and you're sitting there and you're like, how did that have anything to do with what I'm talking about? That's kind of what this is saying. It's saying that if they're independent, if they have nothing to do with each other, then basically if I tell you that one of them happens, that doesn't give you any information as to where the other happened, and therefore the probability that E happens given that F happens is just the probability of E. And so now I can cross multiply here and get that the probability of E intersection F is equal to the probability of E multiplied by the probability of F. So that's where it comes from. So before, when I was multiplying back up here, like this, it's because they're independent events. These ones. Okay. So that's that. So that's just kind of independent events. That's more so like a little bit of like a formal approach. I might do a couple of these ones just to... Yeah, I might just do maybe one long one and then I can leave it at that. Okay, so let's do like question 9. Question 9 is a little bit weird. So it says a green 6-sided die and a red 6-sided die, so just normal dice, are rolled. E is the event that the score on the green die is 1. F is the event that the total on the 2 dice is 7. Investigate if E and F are independent. Okay? So what you want to know is, okay, is the probability of F given E equal to the probability of F? Okay? So, basically, I'm just going to do this really fast. You're just adding up all the numbers, okay? So you just have nothing here. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then you just add up all the numbers. Okay, so it's 2. Nine, 10. Sorry. 6 and 7. Okay, so what I just did a quick table here that shows that, say this is the red die, this is the green. So remember, so first of all, what's the probability that F happens, just in general? The probability that F happens, so the probability that we get a 7. So how many 7s are there? 1, 2, 3, 4, 5, 6. So there's 6 of them. And there's 36 total combinations. So the chance that F happens is 1 in 6. So what I want to know is, the probability that F given E is equal to the probability of F. So is this equal to this? Or not? So what you can do is you can say, okay, well, the probability of E, so E is basically, you get, the green die is 1. So the green die is 1. So we're only looking at this. Okay? So what's the chance that we roll a 7 if we definitely roll a 1? Well, the chance is just 1 in 6. And therefore, they are independent events. Okay? Which hopefully makes sense, and that's what it should be if it's a 7, because if it actually doesn't matter what you roll the first time, because there's only one thing that you can roll the second time to give you 7. Whereas with 8, if I want to get a total of 8, I can't roll a 1. If I roll a 1, then you can probably see here, none of these are 8. So I can't get 8 if I roll a 1. But the thing is, it actually, because 7 is a little bit of a weird number, or kind of like a distinct number, basically you can get 7 the whole time. So that's why they're independent, because it actually doesn't matter what you roll the first time. You can always, there's only one chance you get a 7 then the second time. So it actually ends up not mattering. Okay, which is quite like interesting. Okay, so that is that one. So I will finish this by doing some binomial trials. Okay. All right. So binomial or Bernoulli, whichever your teacher calls it, I suppose. I just typically say binomial. So the binomial trials is basically, if you want to know what's the chances that 3 things will happen if you have 10 goes of it, you use Bernoulli trials. Now that might sound very hand-wavy, because it is, but it's just a thing of like, if they said, okay, Harry has a 60% chance of scoring a penalty and a 40% chance of missing, what's the chances that he scores 6 out of 10? This is when you will use your Bernoulli trials, okay? Or your binomial distribution. So it's the same thing. It's a formula in the log tables. But basically, you just sit there and you say, okay, so it'll be the same thing of like, if I ring Adam's house, he has a 70% chance of picking up. What's the chance that he picks up exactly 5 times out of 7 times in a week? That's, again, you're using your Bernoulli trials. So the formula for this is very simple. It's N, R, which is your choosing, PR, Q to the N minus R. Okay? So remember, it's just N, CR, PR, Q, N minus R, where this P is basically, it does happen. Q is that it doesn't. So typically, Q is just equal to 1 minus P. So obviously, if there's a 70% chance of it happening, then there's a 30% chance of it not happening. How did you get 30? You did 100% minus 70. So that's kind of what's going on here. Okay? All right, let's do a couple of questions. So it says, Leah is the team's penalty taker. Last season, she took 20 penalties and scored 16 times. Use the relative frequency as the probability of scoring. So her relative frequency for this question is her probability of scoring is how many times did she score? 16. Out of how many times? 20. That means it's 0.8. So her relative frequency is 0.8. So we're just going to take this, that's the probability. Grant. It says, during the next season, she takes 8 penalties. Find the probability that she scores the first 6 penalties, but misses the last 2. So the first one, you say, okay, what's the chance that she scores her first 6? So her first 6, she scores. So it's 0.8, 0.8, 0.8, 0.8, 0.8, 0.8, but then she misses the last 2, so it's 0.2 and 0.2. And you multiply all these together. Okay? And you get whatever you get. That's it. Because you know she scored the first 6 and she missed the last 2. So this thing is basically if you don't know what the order happens, and that's the main thing. If I said, okay, she scores 6 out of 8, what's the chance that happens? Well, then she could have missed the last 2, she could have missed the first 2, she could have missed the first one, she could have missed the 7th one. It's these sort of things that you don't know. Okay, so that's, actually, you know what, I might just do that out of my calculator just to see. So that's 0.8 to the power of 6 times 0.04. 04. Okay, so this is going to be 0.0105. Okay, so that's the probability that happens. Then it says she scores exactly 6 penalties. So find the probability that she scores exactly 6. Well, now this is where you'll use your choosing. So first of all, there's 8 penalties and she scores 6 of them. So basically, if you're wondering what's going on, this is just the number of ways you can arrange 6 out of 8 things, basically. So back a couple of videos ago when we were doing choosing and stuff like that, and we were saying, oh, that's the number of times you can arrange things. That's basically what this number is. So 8C6, that's just saying that if you how many different ways you can kind of miss 2 penalties out of 8. Basically, so you can miss the first and the second, first and the third, first and the fourth, first and the fifth. This thing is just adding up all those. Okay. This then, what you're doing is you're saying, okay, well, P is the chance that it does happen. So it's 0.8, that needs to happen 6 times. And then she needs to miss twice. So she misses 20% of the time and she does it twice. So then if you just plug this into your calculator, you will get C6. This now becomes 0.29. Okay? So it's much more likely that she'll score 6. Okay? And then finally it says, find the chance that she'll score 6 or more. So first of all, the chance that she scores 6 is, we just calculated there, 0.29. the probability that she scores 6 or more. So I need to find what the probability of that she scores 7 is. So 7, I'm going to do the exact same thing, but wherever there's a 6, I'm just going to change it to 7. So it's 8C7, 0.8 times 7 times 0.2 to the power of 1. Why? Because it only happens once. So just be careful with that. So 8C7 should just be 8, yeah, times 0.8 to the power of 7 times 0.2. So this is going to be 0.336. And then the probability that she scores all 8, well, that's just going to be 0.8 to the power of 8. Because if we go back up here, if she scores all 8, then I know that she scores. There's no other order. There's no missing. So there's no order you have to worry about. So it's just 0.8 times 0.8 times 0.8 times 0.8 times 0.8 times 0.8. And you just do that. So it's just 0.8 to the power of 8. And that's going to be 0.168. So if I do 0.168 plus 0.336 plus 0.29, the total probability that she'll score 6 or more is 0.794. Like that. Okay, so that's that. Now there's one more thing that I want to do. I'm trying to find a question that says it, or else I will just do it myself. Okay, I'll just do it myself. All right. So so I'll do one of these questions. It says, how many times must a fair coin be flipped in order to ensure that there is at least a 99% chance of getting at least one tail? So again, you want the probability of one tail to be greater than 99%. What's that the same thing as saying as? That means that the probability of getting all heads has to be less than 1%. So the probability of getting n heads is equal to a half to the power of n. Okay, so if I get one of them, it's just a half. If I get two of them, it's a half times a half. So a half to the power of 2. If it's 3 of them, it's a half times a half times a half, all to the power of 3, and so on and so on. And so it's just this. So I want to know, when is this less than 0.01? All right, how are we going to solve this? Does anybody know? You might sit there and say, I have absolutely no idea. I would just start plugging in numbers. That is a valid way of doing it. I'm being dead serious. You absolutely can just plug in, a half to the power of 5, 6, 7, until you get less than 0.01. There's a bit of a better way of doing it though. It's using logs. So always what you do is you just equal it. So just equal a half to the power of n. Sorry, I don't know why I did that. To the power of n, just equal it to 0.01. And now just solve it. So if I do logs on both sides, I get n is equal to log to the base a half, 0.01. Log to the base a half, 0.01. So it's going to be log to 0.5.01. I get this. I get 6.64. So now, if n is equal to 6.64, I get exactly 0.01. I want to know, what value does n have to be for me to be less than 0.01? So do you think n has to go up to 7, or does n have to go down to 6? Now again, pause the video and think about it. Just sit there and be like, okay, so I want to say, okay, if I flip a coin 6 or 7 times, I know, so obviously the answer can't be 6.67 because you're flipping a coin. You can't flip a coin 0.64 times. So it's either 6 or it's 7. So if I flip the coin 6 times, will I get bigger or less than 0.01? And if I flip the coin 7 times, will I get less or more than 0.01? The answer is you want to round up. So the answer is n equals 7. Because you know that if you plug in 6, you're going to get a little bit higher than 0.01. And if you plug in 7, you get a little bit less. So n equals 7 is the first number that would be just less than 0.01. And therefore, you need to do it 7 times before you can guarantee that you get that you're more than 99% chance that you'll at least get one tail. Okay? All right. Very last one, I'm just going to make up a question. Just because I want to, because this thing does come up. I'm surprised. Maybe the book has one, but I can't see it. Anyways, basically, so let's say you ring someone 7 days in the week, and the chance that they pick up is 40%. That they'll pick up, and then there's a 60% chance that they won't. The question says, what is the chance that they will pick up exactly 3 times, given that they picked up on Sunday? So they picked up on Sunday, and what's the chance that they picked up 3 times exactly, Monday to Sunday, and you know that they picked up on Sunday? Okay, so there's 7 things again. So you know here they definitely picked up. Grand. And I want to know that they picked up 3 times exactly. So 1 was on Sunday. That means that 2 times they have to pick up on Monday to Saturday. So what I want to know is, I want to say, okay, what's the chance that they pick up exactly 2 and 6 times? So again, that's your 6 C2 times the chance they picked up. That's 0.4. That happens twice. The chance that they didn't pick up is 0.6, and that happens 4 times. And then I have to multiply that by 0.4. Because I know they picked up on the last day. Okay? If you plug this into your calculator, you will get this times 0.4 squared times 0.6 to the power 4 times 0.4. Wait, oh, sorry. Times 0.4. So I end up that this is just going to be 0.124416. Okay, so that's the last thing I want to cover. So just if they say, okay, given that it happened on one of these days, then how do you figure out the rest of them? Okay, and this would be the exact same procedure if they told you on Monday they picked up, or on Tuesday they picked up, or Wednesday or whatever. Doesn't matter. You would do the exact same thing. Okay, so they picked up 3 times, they picked up on Sunday. So you used your binomial for the first 6 days because they picked up exactly twice in the 6 days. And therefore you calculate out that, and then you multiply 0.4 because that's the chance that they picked up on the last day. Okay. All right. Okay, I think I will leave that there. So yeah, the next thing I'm going to go over is the normal distribution. So perfect. Thank you very much for paying attention, and I think I'll leave it off there. So I'll see you in the next video. Thanks so much.